me say comparison of flat, free, and projective. Okay, so so the big theorem that I want to prove is that if M is finitely presented, is a finitely presented R module, and R is a local ring, then so M is free if and only if M is projective, if and only if M is flat. Okay, so all these things collapse in this case. So and so we're going to essentially show that M being flat is equivalent to M being free, and M being projective is equivalent to M being free. And so we'll work with the hypothesis. So we work. Okay, so I'm not going to prove exactly this theorem. We will use another thing. We will use that. So we'll use that M is. So this is slightly more general than what I'm going to prove. M is finitely generated. And R is Noetherian. So in this case, one of the things that happens is that you'll have M, so you'll have some surjective map like this. That's what it means to be finitely generated. And then using Noetherianity, the kernel here. So you want this thing. So you want this to be finitely generated. And you need this to apply Nakayama's lemma. Okay, so this is one of the things that you'll want to do. And you also kind of want, you'll see what comes up, okay? So note that, so I'm just showing here that finitely generated in Noetherian implies finitely presented. Okay, so that being said, let me start with the first part, so theorem. Okay, so let Rm be a local ring. Okay, and we're going to let M be a finitely generated projective R module. Okay. Let's do finitely. Let me see it this way. I want to write it a different way. Let M be a finitely generated R module. R module. Okay, if M is projective, this implies that M is free. Okay. Okay, so and I guess I need to say be a local, and then I'm going to put Noetherian here. Here. So I'm gonna need to get a kernel that's finitely generated. Okay, so here's the proof. All right, so here's the proof. Okay, so we're going to take M bar, and it's going to be defined to be M mod the maximal ideal here. So this is a finite dimensional. It is a finite dimensional K vector space. Where K is R mod the maximal ideal. Okay, and so we're going to take it. So here we're going to have generators. So it'll have a basis. So M has a basis. M bar has a basis. X1 bar, X2 bar, We can say xn bar. Okay, so by Nakayama, these lift to generators. So these lift to generators. X1 xn of m. So they're generators, they're not necessarily a basis. Okay? So this gives us our presentation, right? So we have r to the n. There's a surjective map here, phi to m. Okay, and this goes to 0. And here we have phi of the basis vector going to xi. Okay, and then there's the kernel here. And this goes like this. Okay, and so by the so here this is finitely generated by the Noetherian by Noetherianity. Okay, so R being a Noetherian ring means R to the n is a Noetherian module, which means the submodules are finitely generated, and this is a submodule. Okay, so this is so in particular, Nakayama is in play for this thing. Okay, so now the one thing I haven't used so far, this is kind of just I'm using the finiteness hypotheses. The one thing that I haven't used is I haven't used that m is projective. Okay, and so we're going to use that to show we're going to take the so we're going to split the sequence. So since m is projective, okay, so since what happened here? Oh, I don't want that. Go away. What the heck? All right, I don't know how to get rid of that. Oh well. Delete. There we go. Okay. Okay, so now I'm gonna use projectivity here. So since m is projective, the exact sequence, so this exact sequence, sequence star splits. Okay, and so we have 0. This goes like this. This goes to m. Oh, sorry, this doesn't go to m. This goes to r to the n. R to the n. And this goes to m. This was phi. And then we have some splitting here, which we'll call psi. This psi is not the same. Did I use psi before? I didn't use psi before, did I? No. Okay. So yeah. So this sequence splits. In particular, we have that r to the n is isomorphic to this thing, direct sum psi of m. Okay, so psi of m. So psi of m is isomorphic to m. Okay, so it's the direct sum of these two pieces. Okay, and now we can reduce everything mod m. Okay, so did I say what k was? Did I say k is this? Okay, k is r mod m. And so what I'm going to do is I'm just going to tensor everything with k. R to the n, tensor with k. Okay, so this is a direct sum, so we get to do the tensor product on each of the factors. So we're tensoring over r. Oh, kernel. Direct sum. And then we have m, and then we have tensor over r with k. Okay, so again, remember that this is r mod m, and so recall. Stop. All right. So recall that here that n is isomorphic to, so here n tensor R mod m over R. So this is isomorphic to n mod m R, or this thing. So you have that when you tensor with something mod and ideal, it's just this n mod the ideal times n. Okay, so that was one thing that we had. Okay, so and remember that this thing here is k in our situation. Okay, so what is this thing? Okay, so this is isomorphic to, so this is m bar, right? So this is isomorphic to k to the n, right? So this is just a vector space of dimension n. This is also isomorphic to k to the n. And we have some other piece here, some vector space. Okay, so if I have a summand and I have two vector spaces, right, where you know, the two vector spaces are the same dimension, that means that this thing has to be 0. Okay, so in particular, we have that the kernel of phi tensor Rk, right? So this is 0. This is cur phi. And now I'm going to use Nakayama again. And so this is 0. So this means that, so we have, in terms of Nakayama, cur phi is equal to the maximal ideal times the kernel of phi, which implies that the kernel of phi is 0. So this is by Nakayama. Okay, and now let's go back to our sequence here. So let's maybe even this one here. Maybe I can do it in another color. So in this sequence here, this thing is 0. So now we have an exact sequence, and it shows that this map is injective and it's surjective, so it's isomorphic. So this all the way back up. So this tells us that m is isomorphic to r to the n. So m is free. All right, and that concludes the proof. Okay, so we showed that n being projective implies free. We already know that free implied projective, and so and the hypothesis is that it's over a local ring, right, where this kernel, you can arrange for this kernel in this sequence here to be finitely generated. Once you get it to be finitely generated, then you can apply Nakayama. Okay. So okay, so let's do some corollaries here. So corollary. So finitely finitely generated. So 1 finitely generated projective modules over Noetherian rings are locally free. Stock locally free. Okay, so if m is projective, right? So this means that m projective under these hypotheses, right? So this is kind of the motto that I'm writing here, is that MP is going to be isomorphic to RP to some power here. Okay, so when you localize a projective module, it's going to become a free module. Okay, so the other thing that we get is that so this one, the proof of this one is immediate. So the proof of this one is immediate because after localizing, you have a finitely generated projective module over a local ring. So the proof of this is that after localizing, you are immediately in the hypotheses of the previous theorem. And like I said before, you can so you can drop this Noetherianity hypothesis by if you assume that this thing is finitely presented, right? So that was another way to get around that. Okay. So okay, so another consequence is that finitely generated projective modules over Noetherian rings are flat. Okay, so let me do the proof of the second one. So proof of 2. Okay, so flatness is a local property. A local property. Okay, and in free, and so locally, you know, MP is isomorphic to RP to some power, which implies that MP. So it's locally free, right? And free implies flat. And since free implies flat, we have that MP is a flat. MP is a flat RP module for every P in spec R. Hence it's going to be flat. Hence it is flat. Okay, so we're using the flatness as a local property. Okay, so we showed that it's flat locally. So since it's flat locally, it's flat. Okie dokie. All right. So, all right. Okay, so the last thing that I want to do is I want to show that okay, so I'm gonna do a trick. Okay, so I'm gonna prove. So let me do a theorem.